Hello, am I ready? Hello.
Yes, sir, you are audible now.
Yes, sir. Thank you, sir. Thank you. Is my PPT visible?
Yes, sir. Visible.
Okay, thank you. So what we left from if P equal to NP, if you prove P equal to NP, then you're able to break the cryptography also. Suppose if P equal to not NP, then we need to go each and every algorithm what we left, and even though if you do all these operations or options, it will take end of this world. So it is unsolvable. Are we able to accept all these problems we cannot solve? Definitely we need to accept, but we can produce mathematical axioms to understand these type of problems. So this is very good opportunity for mathematics department and theoretical computation. They can do much more contribution in quantum computing. So if you don't know about physics, if you don't know about computer, no issue. You can focus on theoretical computer science and to prove these axioms. Okay. So how to compare a easy and hard problem? Okay. So this is a illustration what I want to show with you. So if you, this is your input size, the x-axis is your input size. Maybe I can use pointer. So x-axis is your input size. You need to increase number of elements. So we start from element 1. In the element 1, the function is n square, it will go in this way. If function is linear, it will go in this blue line. If function is log, it will go in this orange line. So initially there is no much more difference in input 1, but if you gradually see, if you increase 15, so n square goes somewhere else. Okay, log and linear will go next to next, but you can see the difference in 71. So whenever if you increase input size, then you can easily able to compare your problem is whether in easy category or hard category. Okay. So what is the best way to check our problem? We need to increase the number of input. So what happens if you increase number of input? You can see from y-axis, the time is also get increased. The memory resource also get increased. So this will create problem for you. Suppose if you want to solve your problem, you need to give as less time as for your problem, less memory for your problem. Okay, then only you can say your algorithm is efficient one. If you keep on increase the function difficulty, take an example of 2 power n and 5 power n. Okay, you see, based upon your function growth rate, the classification become much more harder, right? So keep on increase your inputs. Now I increased, you can see the difference. I increase the timeline and also memory. You can see the clear difference. In previous slide, you can see the difference between this orange and this blue is somewhat there. Difference is somewhat there. But if you keep on increase your time and memory, it almost appears to be equal. But you can see the huge difference between these two with your n square. Okay. In the same way, if you keep on increasing your time lap, then apparently you can see the difference between n to the power 5 and 2 to the power n and 5 to the power n. So keep on increase, you're able to see only to the 2 power n and 5 power n. So if you gradually increase to the exponential time, then you can see the clear picture of your classification. Okay, so these problems are in large scale. These problems are called linear. Some problems are like exponential. So if you keep on increase, At one point, you can see polynomial growth rate is greater than exponential growth rate. Okay, so this green belongs to a exponential function. This yellow belongs to polynomial growth. But sometimes this polynomial appear to be much more difficult when compared to exponential. Okay, this is the crossover point. You can see these are crossover point. So this will give you clue about what type of algorithm you have. So what are the options we do have? Okay, so we have all these classification, sorting problem, multiplication, addition. If you want to do spell check in your Word or searching your files, okay, or arranging your documents or solving Rubik cube or doing spreadsheet, graph and chart, all these type of day-to-day task problem or belongs to polynomial time. So it could be solved efficiently, it could be checked efficiently. Okay, where some problems are called BQP. So bounded error quantum polynomial. So this is the new classification we have in computational theory. Okay, even for computer science faculty or IT faculty, they never heard about this because it belongs to quantum. So take an example of factorization or Boolean satisfiability problem or traveling salesman problem or playing Super Mario. Okay, knapsack problem. So all these problem will belongs to BQP. So here you require quantum computer to solve. So classical problem P, you are able to solve with normal classical computer. But if you want to solve these BQP problems, okay, classification, you need quantum computers. So some problems are there called NP. We already covered. Okay, so not polynomial time. So it is verified efficiently, but you cannot solve. You cannot solve efficiently. So we need a much more faster computer. So that is why we are going for quantum. Okay. So some problems like chess, Go, QSAT. So these problem belongs to P space or exponential space. So there is no solution in reasonable amount of time or space. Okay. And you are not able to verify the solution also. So some problems are much more harder than P. Okay. P space and exponential, even the quantum computer not able to solve those kind of problems. Whether this slide is understandable, can we go for next one? So all these problems belongs to BQP class. Shall we go? Okay, fine. So you need to ask this question, whether quantum computer can solve everything. The answer is obviously no. The answer is obviously no. Yeah, NP means verified efficiently, but not able to solve. So those problems are solvable. Take an example of NP complete problem. So this is maximally hard problem in the case of in the class of NP, are believed to hard to solve. But a given solution is, it is easy to check whether it is correct or wrong. Okay, take an example of satisfiability problem. A equal to 1 or B equal to 0 or C equal to 1, and you are using AND logic. B equal to 1 or C equal to 0 or D equal to 1, and again you are using AND logic. C equal to 1 or D equal to 0 or E equal to 1, and you are using AND logic. So simultaneously, you can combine all these Boolean logic together. So combination of Boolean logic. So these kind of problem are their solution to satisfy this Boolean formula. We need to check. Okay. So this belongs to NP hard. In the same way, if you have click problem, okay, in your social media network, can I find the largest list of people who all know each other? So it is very difficult. So this problem belongs to click problem. Suppose if you have, let's say 150 connections in your Facebook, okay? If you need to check whether any person is there within your network who know remaining 149. So this type of problem belongs to click problem. So this problem belongs to class NP. Okay. So take an example of set theory. So this is subset problem. So this is one subset, this is one subset, and this is one subset. So if you are giving subset problem, okay. So is there any non-empty subset with the sum equal to 0? Yes, NP problem also very difficult for quantum. NP hard also very difficult for quantum. Okay. Could all permutation and combination to be set up into one mighty superposition for a quantum computer to check? So this is the essence. Suppose if you have multiple permutation, combination or options available for a given problem, then the superposition and entanglement will help you to solve in parallel fashion. So you can verify with your question. Okay. So only few, that also it is in R&D level. You cannot solve all NP hard problem using quantum computer. So we'll discuss those problems, what are possible and feasible. Take an example of what a quantum computer cannot do. Okay. So normally quantum computer having this capacity of parallelism. Okay. So it feels easy to think a power of a quantum computer as a gazillion parallel computers exploring all possibility at once to find the correct answer exponentially faster. Take an example of superposition. So if you have 1000 qubits, if you are making in superposition, you can represent enormous amount of information and you can do parallel computing. But in truth, checking all possible parallel states is not possible in a quantum computer, because if you do measurement, it will check randomly. It will fall only random states. Okay. And also a quantum computer also needs a few tries before it arrives at an answer. So each and every time it will do trial and error. And in each and every trial and error, you'll get multiple answer. So correct answers are there, and bunch of wrong answer combinations also there, because you cannot verify which one is correct, which one is wrong. You need to run for multiple times. So this is one problem quantum computer facing. Not all problems can be speeded up with quantum computers, only certain problems. To identify your problem, you need to do this classification. So this topic will help you to fine tune your research problem. Suppose if you are doing any problem using quantum computer in computer science, what you do, take your problem, go to a mathematician or mathematics faculty, do a check of this computational complexity. Okay, if it is really computational complex, then only go for quantum. So this is one suggestion I can give for you. And if you want to check the quantum algorithm efficiency, you need to ask these basic two questions. Efficiency comes from choosing the right problem, okay, or manipulating probabilities. You need to do so many manipulations in your quantum algorithm. So this is like a cheating. Okay. So most of the time we know the solution, we know the answer to do trial and error, right? So we need to do manipulation about our amplitudes in order to get correct solution. Okay. So for that, you need to use two principles, superposition and entanglement, to do all this stuff. And this is the quantum domain we need to focus. BQP, a new type of complexity class apart from class P and class NP. Okay. So this will come under bounded error quantum polynomial time. So the abbreviation of BQP stands for bounded error quantum polynomial time. Okay. So it is proposed by Ethan Briston, defined in 1993, along with Umesh Vazirani. So there is one famous algorithm which is called Vazirani algorithm. So if you have time, please go and check. So he is an Indian origin, now working at US. They both laid foundation of quantum complexity, right? So simple problems like yes or no, decision problems can be solved by quantum computers, and it will take polynomial time. So this is groundbreaking. This is groundbreaking. Because if you want to make decision yes or no, you need to do sometimes randomly. Because we don't know what is the right option for us. In most of our lifetime, we take a random decision. Okay, computer cannot do random because you need to give each and every input for it. Okay, so it will create some errors, but it will lie within the certain limit. So this type of complexity class will make errors because it involved with randomness. So BQP contains P, but what we don't know whether NP also contained in BQP. We don't know this question exactly. We need to investigate. Wait a second. I try to answer your question. No, go HPC first. Even though if you go for HPC, some problems you cannot solve. Only quantum will help you if something randomness is there. Okay. So if your problem contains randomness or multiple permutation combination, please go for quantum rather than classical. Even though if you go for HPC, it won't solve. The classification remains same. Random means solution may also change. Yeah, exactly. So if you are introducing randomness, solution will definitely change. That is why you got both correct answer and wrong answer. But in classical, you only always get correct answer, no wrong answer. So according to your logic, you will get correct answer. So that is the basic difference. QC can solve and give approximation problem. Exactly. So if your problem involved with approximation, okay, quantum will solve. QC also solve, but approximation range is not that much accurate. So all approximate solution will give approximate answers, right? But when you compare accuracy, quantum will much more better, much in terms better terms. Okay. So how to measure complexity? We already discussed. We need to use languages and function. So people who studied complexity theory or theory of computation, they can understand. So I'll mention the subject name if you have time. If you are from non-computer science, so go and ask theory of computation. So in previous lecture, Professor Gines took this topic, theory of computation. Go and refer this QT-05. Okay. So basically, complexity measures of algorithm includes running time and usage of memory space. We already discussed in previous slide. Okay. So whenever the given problem is A, the time complexity is denoted by T of n. So if there exists an algorithm that solves your problem in time T of n for length n inputs. So here the important concept is what is your length of input? What is your length of input? If you keep increasing your input, then you need to calculate how much time it will take. So this is one aspect. The second aspect, for each and every problem A is of space complexity S of n. If there is exists an algorithm that solves A in space S of n for all length n inputs. So again, it entirely depends upon your length of your input. So how much time it took and how much space it takes you need to calculate. So this will give a measurement for your algorithm, complexity measurement. Okay. So based upon this, you can classify your algorithm in different category. We already discussed. So this is the mathematical definition of complexity class P. So that is why most of the time I avoided. All right. For each and every decision problem or language L is in P category if there exists a constant K greater than greater than or equal to 1 and a multi-tape DTM deterministic Turing machine of M states that for any input X belongs to L if it belongs to M except X in O of big O of n power k time, and X not belongs to your language. So L belongs to your language, X is your input, and this is called machine. M is called machine, will reject X in O n k of time. So in simple terms, I want to describe. So this is your machine. This is your Turing machine. So let's say this is M. Okay. Suppose if you are giving X, as an input for your Turing machine. So sometimes this machine will accept. Sometimes this machine will accept reject. So this is what they described over here. Okay. So many natural problems belongs to this complexity class P. So most of the day-to-day our task belongs to class P. Maybe during lack of time, I will show Turing machine because we are running out of time. If time permits, I will cover all this stuff. So this is Turing machine. So this is a model. We built a physical model of Turing machine where you can see tape on both sides, like a tape recorder you can imagine. So here it contains all your inputs or instruction. Okay, according to the instruction, this head will move. Okay. So this is the abstract way. So this is your infinite tape. So infinite tape contains input and instructions. Okay. Whenever it got instruction, it will do all operation. So it will read from this. It will write in this tape. So it will do both actions. So according to the input, the state will change. So according to the instruction, state will change. So if anybody able to recall about Professor Giney's class, suppose if you are using washing machine. So washing machine, if you switch on, so it will go from off state to on state. So imagine like this. If you switch on, suppose if you press clean button or you can say wash button, okay. So it will go on state to some other state. Wash state. Okay. So from wash state, if you set 10 minutes, from wash, it will go for dry. Imagine like this. So from wash, it will go for dry. So this is the physical state we are representing in a logical way. So your computer also do the same thing. So each and every time your input data will get changed according to the process. So this is abstract model. Okay, so all these instructions are loaded over here in universal Turing machine. So it will read and write your infinite tape. So here you can see implementation of your Turing machine. So this is a abstract concept. Okay, this is not a real machine. It is an abstract concept to understand. So this is an example for quantum Turing machine. So in previous diagram, we have only one input tape. So here we have multiple input tapes. Take an example of this is read-only memory. Read-only memory. Sometimes if you are using ROM, you can use it. Sometimes if you are using RAM, you can use this classical working tape. Suppose if you are using qubit, you can consider like another tape. So this is a multi-state, multi-tape setup Turing machine. So this is quantum Turing machine. You can add quantum Turing machine. So you can visualize your quantum computing in such a way. It is an abstract model. Any doubt within this slide or previous slide? If you have, you can ask me. Is it clear? Shall we move? Okay, thank you. So you need to ask these basic two questions. Can the evolution of quantum system to be simulated efficiently on classical computer? Can you do so? What is the answer for this question? What is the answer? We cannot. Okay. So whatever you are building, any powerful classical computer, it cannot do evolution of a quantum system. You cannot simulate. You cannot simulate quantum system using classical computer. So you can ask this question. There are so many quantum simulators are there. Take an example of IBM Qiskit. Where you can simulate all these quantum system until up to 30 qubits. So beyond 30 qubits, you are not able to simulate. Okay. Suppose in future, if they are building so powerful supercomputer, you are not able to do over 50 qubits forever. Because each and every qubit involved with randomness, permutation, combination, infinite amount of combination. You cannot able to simulate using your classical. This is the important word. You cannot do efficient simulation. So even though you are able to do simulation, it is not an efficient way because you have limitation. Okay. So take an example of second question. How hard is to approximate interesting properties of a quantum system? For an example of ground state. Okay. This is also very, very limited. For a single particle, it could be easy. For a multiple particle, for a molecule, for a chemical reaction, it become difficult. I'll check question. Yes. Possible to simulate, but cannot. Can you redefine your question? Is it so? It is possible to simulate? Yes, it is possible. But the question is, it is not efficiently able to simulate. So simulation is possible in classical, but not efficient. So we have some physical limitation. Yeah. We have physical limitation. Exactly. So this is the classification I want to discuss. So if you want to define quantum complexity theory, we can start from BQP, consisting of all languages that could be decided in polynomial time by fully functional quantum computer. So if you want to define in mathematical way, okay, this is very beyond the scope of this lecture. One can prove bounded polynomial probability belongs to BQP, belongs to P space. Yes, exactly. I'll check question one more time. Limitation exists for each and every system, but it can do more possible computation in quantum. So that is why. So if you have some much better scope, you can go for the device. So if some computer evolve after quantum computer, if it solves better than quantum, you'll go for that system, that hardware, because it have additional capacity. Have additional capacity. Yes, sir. Thanks. Already we discussed, there are problems that cannot be solved by a Turing machine in any finite amount of time. That is called undecidable problem. Suppose if we got confusion, we don't know which dress to select. Suppose if we have multiple options and all these options are equally favorable, then it becomes more undecidable. Okay, for humans it becomes more undecidable. Then think about a machine don't know on what parameter to select or choose on its own. Okay, so this example leads to halt problem. So take an example of a halt c comma x equal to 1 if the Turing machine who chose code c halts in finite time on input x. So this is very important for any algorithm to halt at some point. But if you don't know where you want to go after your halt, it will stuck forever. Okay, so your algorithm will stuck forever if your problem belongs to undecidable category. So some person not able to decide, right? They will stuck while taking a simple decision if it is very tough for them. So again, the concept is same. Let's see what is the best resource I can provide. I don't want to bore you with all this mathematical. Yes. So this one is easy for you. So if you are looking at landscape of complexity, so polynomial time problem belongs to BPP classification. So in same way, polynomial time also belongs to NP. In same way, polynomial time belongs to P space. So comparatively, space problem is very difficult. Very difficult. Okay. So P is very easy and P space is most difficult problem. In generally, we do not have any technique to show a problem that does not lie in a complexity class. So it is much more debatable. So this year they will classify in this way. Next year they will classify in very different way. So new type of classification will come. Okay. So take an example of riding a car in very smooth road. It is very easy. Okay. So riding a car in Bangalore traffic is very tough. So the problem is same, but based upon the scenario, based upon the complexity, it becomes more difficult. Okay. So driving in a particular road during a daytime is easy, but driving the same car during nighttime tends to be much more difficult. Okay. Take an example of driving the car in daytime during normal sunny day, but if there is a stormy weather, if there is a heavy rain, then it becomes much more complex. So adding one parameter, changes in one parameter, changes in your input, okay, changes in your input, the situation become entirely difficult. The complexity become entirely new. So you need to think in such a way. So if you are adding one more complexity, one more parameter, it will become much more difficult. Everyone, sir, in every city, if city is growing, traffic is there. If traffic is there, it means city is growing. Okay. Yes. Yes. Because Bangalore is so flourishing, so people keep on moving there. Life is thriving, right? That is the reason. So for this, what we can do reduction. So we need to do reduction technique in order to solve a hard problem. So you can apply this technique in our real life also. Suppose if you are implementing metro, monorail, this hyperloop, it will reduce the traffic. So you can divert, so you can devise a harder problem into a easier way. So easier problem will take less resource when compared to a large problem, right? So if you have algorithm, which is able to solve in L-easy classification, we are able to reduce the complexity. Okay, so how we are able to reduce complexity? By reducing randomized way, by using quantum or space limited. So that is why they will use this space limited technique. So if you want to control a huge crowd, you can limit the number of permission, you can limit the number of visitor. So take an example of Delhi or any place in India. So most of the time they will allow openly. If it is open space, they will allow without any restriction. So if there is a pilgrimage, okay, take an example of Tirupati, okay, they will limit number of visitor per day. So if you are limiting, you are able to control each and everything, right? Take an example of Bhutan. So each and every month or week per day, they will limit their visitors. Okay, so no country is restricting in such a way, but Bhutan, they are maintaining this restriction to provide a quality tourism. Okay, so same way, if you are doing randomized, as we discussed, meta heuristic problem, okay, permutation and combination. So this will reduce your complexity. So in some cases, if you are introducing randomness for your algorithm, it will reduce your complexity. Okay, so class B problem, then NP class problem, then you have NP hard problem. Okay, take an example of every problem in NP is easier than 3 set problem. So this is a Boolean satisfiability problem. So go and refer if you have time. Okay, such problem are called NP hard. So it is like you can compare like our family. So this is like a individual family. So maintaining individual family is quite easy. So this is like managing state of India, state of one of the Indian state. You can say one of the Indian state, and this is like managing the whole India. Okay, you can put this kind of example to understand. All right, so family, the limited amount of person, you know, each and everything. Okay, it is very easy. The problem occurred in family, able to tackable at least by your level, right? But one of the Indian state, you need to understand the dynamic of that state, what are the problem exist in that state, and it is quite difficult when compared to managing a family. In the same way, managing India, it is like managing multiple countries, in my view, right? Very, very difficult. Even though we are going in right direction, So NP-hard problem are living in this region, and some complexity classes we don't know how to solve it. Okay, and most of the NP problem are over here. So 3-set problem also lies in NP-hard as well as NP. It is like in boundary. So normally if you are comparing with Indian state, most of the problem exists between two states exactly in their boundary lines. Not only between Indian state, between countries, most of the problem occurs in boundaries. Okay, you have much more conflict, you have much more difference of opinion. You can see clearly the entire difference, right? So I try to show the resource where I took from. So in quantum, this is one of the difficult topic to handle, complexity classes. Okay, so I'll provide this resource for you. This is very beautiful note where you can refer. So please look for this notes. And if you are referring John Waters, he is a professor working in Canada teaching quantum for past 30 years. So this is his personal website. So please go to this website and you can find so many resources. There I can see books and courses. Yeah. So if you want to understand the quantum computing, first you need to understand the theory of computing. Okay. So I'll share this link also. I keep it very simple. Actually, the topic is very difficult. I prepared nearly 200 slides. 200 slides because I don't have clue how to conduct class. So anyway, I tried most of the basic stuff. So I'll share this entire slide. Please go in your free time. So if anybody handling theory of computation, this will give a clear idea. This will give you a clear idea. So he will explain the additional complexity of our existing problem. Okay, so understanding theory of computation will give a clear understanding of quantum computing, what you can do much more better. Then, yes. So all this stuff you can see related to complexity, theory of quantum information. Very difficult to explain. It will take multiple years to involve in this quantum information and computation. And I want to highlight one of the IBM courses. If you are interested, I hope all of you have IBM account. You can go for fundamentals of quantum algorithm. So whatever I discussed, everything given in very detailed way in this lecture series. So please go through quantum query algorithm. They will say query model computation and its complexity. Okay. So within 2 hours, covering all this stuff is very, very difficult and challenging. And you can measure the computational cost. So whatever we discussed over here, you can calculate exactly. So component wise. So if you are designing circuit, you're able to compute the cost of it. Okay. So I'll share this link also if you want to directly go for this topic. For all this algorithm analysis part belongs to computational complexity. So if you want to analyze any algorithm, it belongs to computational complexity. So thank you all for patiently listening. So I covered very, very basic stuff. Because teaching approximation theory or heuristic is out of this bound, little difficult to cover all these topics. So once you got exams, you can study on your own. So whatever the resource course I provided, you please go and check. It will contain all these details. So understanding quantum within 10 series is almost impossible. Whatever the lifetime we have, we are able to learn only a fraction about quantum. So according to our domain, we need to streamline. We need to focus. Okay, thank you all.
Thank you so much, sir, for this wonderful session. Thank you.
Thank you, sir. Thank you.